we'll look at turboprop engine. And this is a continuation of shaft engines, where we looked at spark and compression ignition engines, and we went further to look at aircraft propellers. And now we look at turboprop and turboshaft engines. I will present a lecture on aircraft propellers, but now I will look at turboprops. Okay. So as an introduction to turboprop engines, so these are hybrid engines that provides both jet and propeller thrust. And these are actually similar to turbojets engine, except in this arrangement the turbine works through a shaft and a speed reducing gear to turn the propellers. So turboprops, the difference between a piston aircraft engine and a turboprop engine is, in a turboprop the propellers are driven by a turbine, which is different from the piston engine, where you've got reciprocating engine that are connected to a shaft that turn the propellers. So turboprop engine produces two kinds of thrust, one with the propeller and the other one through the exhaust. And the most of the thrust is produced by the propellers. About 85% of the total thrust, forward thrust in this case, is generated by the propellers, whereas the exhaust contributes a low amount, approximately 15%. And this is a schematic of a turboprop engine. You can see you've got the propeller and a gearbox that reduces the speed, and you've got the inlet, so everything is similar to a turbojet. And you've got a turbine, compressors, you've got the combustion chamber, and the exhaust where the nozzle is. Okay, so the propeller will rotate at very low speed compared to the turbine driving it. And that's why you want a gearbox, a reduction gearbox. It has to reduce the speed. The propeller cannot be turned at the same rotational speed as the turbine. And the reason why the speed of the propeller should be low or slow are basically two. The first being large centripetal forces will arise as a result of rotation of the large diameter propeller blades. And these centripetal forces will exert a tensile stress on the hub of the propeller. And if this is not rectified, it could lead to failure. And the other reason has to do with the relative velocity of the propeller tips. Because if the propeller is rotating too fast, I think from aerodynamics, you will learn that the speed at the tips will approach the speed of sound. And as you begin to approach the speed of sound, compressibility effect kicks in, and that leads to generation of wakes, which leads to production of more drag, and therefore reducing the overall efficiency of the propeller. So you can't allow the propeller to rotate very fast. Right, so now let's look at the advantages and disadvantages of a turboprop engine. So the first advantage is these engines have a higher fuel efficiency. So among the engine configuration, turbojets, turbofan and turboshaft, turboprop piston engine. These turboshaft or turboprop engine, these are fuel economic. So for the same amount of thrust, you require less fuel. And these engines are suitable for vertical takeoff and landing. And the Offspring V-22 is one aircraft that uses turboprop engine. And the takeoff thrust, turboprop engine have a higher takeoff thrust that enables aircraft to have a short airfield takeoff. So for all those aircraft that are required to take off from a short airfield, for example from an aircraft carrier, they'll have an engine of this type, and they've got a higher propulsive efficiency for flight speed within 400 miles per hour compared with either turbofan or turbojets. So these basically are some of the advantages of this engine. However, they've got some drawbacks, and one of them is being noise and vibration. And that's why, because of noise and vibration, these engines are not used for passenger aircraft. Passenger aircraft will mostly use a turbofan engine. It's a bit quieter. You don't need a turbo shaft or a turboprop engine because the rotation of the propeller generates a lot of noise, which could be violating existing regulation on noise generation, and you won't find this. So these engines are mostly used in military aircraft, where military bases are usually situated far from cities or where noise could be a significant problem. And the other reason, these engines are only limited to subsonic flight, that is less than 400 miles per hour, and low altitude. So if you need to fly supersonic or transonic, these engines will not work, because from the introduction I said as the speed approaches Mach number equal to 1, there will be compressibility effect. So you don't want your propeller blades to stall, because when they stall, then the lift or the thrust generated will drastically reduce, and you don't want that to happen. And hence you wouldn't want to have this engine if you need to fly faster. And the other reason is because you have a reduction gear to reduce the rotational speed of the turbine, so that the speed of the propeller is within the acceptable limit, and this gearbox will obviously contribute to weight. Hence this engine will usually be heavy, and the heavier the engine, the more drag that aircraft will generate, and the less efficient the engine will be. And the fourth reason is because we've got a gearbox in front of the inlet to the engine. So this gearbox might act as an obstruction to the air intake. Hence the shape of, you need to find a way of designing your intake system, because the intake of like a turbojet and a turbofan, it's open to the free stream. But if you've got an obstruction, then the amount of air that you can ingest will reduce. And if you reduce the amount of air being ingested, then you also reduce the amount of energy that can be extracted from a given amount of fuel. So this is another drawback. Right. So now we'll look at the different modules of a turboprop engine. starting from the intake or the inlet, the compressor, the combustion chamber, and the turbine through to the nozzle. And we'll look at the thermodynamic analysis. Okay? So this sketch shows a turboprop, a single spool turboprop engine together with its temperature entropy diagram. So from here, because this is a single spool, so you can look from the station numbering. A, this is upstream, where you've got atmospheric conditions. Then 2 is entry to the compressor, and 3 is exit to the compressor but entry to the combustion chamber, and 4 is exit to the combustion chamber but entry to the turbine, and 5 is exit to the turbine but entry to the nozzle. 6 is exit to the nozzle and entry to the downstream, that is free stream. So the condition beyond 6 is exactly the same condition as at station number A. Alright, and from here you can tell that the turbine is driving both the compressor and the turbine, and the propeller. And the propeller is, there's a shaft that connects the propeller and the gearbox, because the gearbox will have to reduce the speed so that the propeller turns at a predetermined speed. And from this single spool arrangement, if you look at the temperature entropy diagram, you can tell that temperature, the highest cycle temperature is 4, which is inlet temperature to the turbine. And this is a design parameter because it has to be predetermined in advance, otherwise the material used to build this turbine will not withstand the higher temperature. So you need to know this temperature in advance. And from here, like I've always explained, lines that lie on the same pressure lines will have the same pressure. So pressure P03 is equal to pressure P04. So what does this mean? It means that if we assume ideal conditions, there will be no pressure drop across the combustion chamber, which in reality is not the case. Then PA is equal to P6. It means that the exhaust from the nozzle will expand to atmospheric condition. Hence, these 2 points will still lie on the same pressure line. Right? And now, if we look at the thermodynamic analysis of the intake, where you've got the intake efficiency or isentropic efficiency of the diffuser or inlet, then the ambient temperature and pressure is PA and TA. Then you can get the temperature at entry to the compressor using this formula. And this formula is similar to the formulas that we've looked at under turbojets, turbofans. And the temperature at entry to the compressor is given by this formula, which by now is pretty obvious to all of you, I hope. Then gamma C, this is the gamma on the chord side. So C stands for the chord side. When there's a H, it means anything after the burner. After the combustion chamber, the properties of air will change because air would have been heated and maybe it will have mixed with the exhaust, so it will have different properties. Right, then in the compressor, at the outlet to the compressor, you've got the exit pressure, the total pressure, which will be given by this equation, and the exit temperature to the compressor but entering the combustion chamber will be given by this formula. And obviously this should now be familiar to you. Then the work done the specific work done to drive the compressor, which is also the change in enthalpy. That's why there's a delta HC, that the change in enthalpy will correspond to the specific work done to run the compressor. So it's the difference between the temperature at entry the compressor and exit the compressor multiplied by the specific heat of the cold air which is entering the compressor. And in the combustion chamber, you do the same analysis. If you assume there's a there's a pressure drop, so the pressure at P4 will be equal to a percentage of the pressure drop at P3, and you get this formula. Then if you do an energy balance in the combustion chamber, you can get the fuel-air ratio, which is given by this formula. I've just presented the formula because we've looked at this equation in great length in the previous topics, turbofans and turbojets. Alright, then in the turbine, since in the turbine it's not easy to determine the outlet pressure and temperature, because the turbine drives both the compressor and the propeller for a single spool arrangement. Then the proportion of each is not known in advance, so you don't know how much power is needed to drive the compressor and the propeller. Hence, you have to examine the power transmission from the turbine to the propeller, as has been illustrated in the next slide, this slide. So from this slide, you can tell that the power that is generated at 1, where the turbine is, will be used, and the net power will be equal to the net specific work will be equal to the mechanical efficiency of the turbine. So this eta mt, this is the mechanical efficiency of the turbine. So this will be the available power, like at 1, like efficiency mt multiplied by the specific work of the turbine. So this is the power that is available to drive both the gearbox and the compressor. Then at the compressor, when this power has been used to drive the compressor, the power that will be available to drive the gearbox will be the difference between the power that is available at 1 and the power available at 2. So at 2, this efficiency, mechanical efficiency of the turbine multiplied by the specific work of the turbine minus the specific work needed to drive the compressor divided by the mechanical efficiency of the compressor. So this difference is equal to the power that is available to drive the gearbox. And you have a gearbox efficiency. So the power available at 3 will be the mechanical efficiency of the gearbox multiplied by the power that is available at the gearbox. And this is the power that is available to drive the compressor. So the power that is there to drive the compressor is given by the gearbox efficiency multiplied by the propeller efficiency multiplied by this ratio. Hope, and this is what this slide is trying to explain. So eta mt is the mechanical efficiency of the turbine, eta mc is the mechanical efficiency of the compressor, and eta g is the efficiency of the gearbox. And the propeller efficiency is given by PR. Right? Okay, so from here we can now proceed. Like in the next slide, there is enthalpy-entropy diagram for the expansion process through both the turbine and the exhaust nozzle as shown. So there is an enthalpy-entropy diagram through the expansion process in the nozzle. So from 4, which is entry to the turbine, and 5 is exit to the turbine but entry to the nozzle. Then 6 is exit to the nozzle. So this is the sketch, and these are the enthalpy-entropy diagram. So between 4 and 5, there is this alpha delta H. So this is a ratio of how much enthalpy is lost. So the enthalpy that is available in the nozzle, so delta H then subscript NS, so N is the nozzle, okay? So the enthalpy that is, the change in enthalpy that is available in the nozzle is 1 minus alpha then multiplied by the change in enthalpy, and this is illustrated here on this sketch. So between 4 and 5, on the left hand side of this sketch, there will be an enthalpy decrease, and that is being taken care of by this subscript, okay? Hence so this equation can be, you can now substitute numbers. So the change in enthalpy between state 4 and state 5 is given by equation 6, where you've just substituted, like, since PA is equal to P5, which you can substitute and use the isentropic relation for temperature, and you'll get this change. And the exhaust speed will be given by this formula. So eta N is the nozzle efficiency, and this ratio is the change in enthalpy of the nozzle, or the fraction of change in enthalpy that would be available if the isentropic turbine had the actual pressure ratio, okay? And the propeller efficiency is related to the propeller power by this relation. So the propeller thrust, the propeller thrust is equal to the mass flow multiplied by the propeller efficiency multiplied by the gearbox efficiency, then the shaft power divided by the flight speed. And the shaft power is given by this formula. Now, if you substitute this formula, the shaft power, if you substitute it in the above formula for the propeller thrust, then you get equation 7. So equation 7 is merely a substitution where you substitute the shaft power into the propeller formula, the propeller thrust. So you do that, you get equation 7. So this is the thrust generated by the propeller, which is about 85% of the total thrust that a turboprop will produce. And now the nozzle thrust, so T with a subscript N is a nozzle thrust. So this is the thrust that is generated by the exhaust gas that are leaving the nozzle, and this is given by the mass flow, then open bracket 1 plus the fuel air ratio multiplied by the bleed ratio. So B is the blade, the air that is blade in the compressor. Then this you multiply it by the exhaust speed, then minus the flight speed. And therefore the total thrust will be equal to the propeller thrust plus the nozzle thrust. And the specific thrust, which is equal to the total thrust divided by the mass flow, is given by equation 8. So equation 8 is merely you substitute, because we know equation 7, which is the propeller thrust, and there's the nozzle thrust So you substitute, you add these two, then divide by the mass flow, then you get equation 8. This is not complicated mathematics, it's just an application of the basic principles. And in here, what is in they've substituted back, like here on this formula for the nozzle thrust, there's the exhaust speed, capital U subscript E. So this is the nozzle, this is the exhaust speed, which is given by this equation here, the exhaust speed. So what they resubstituted it back. That's why this equation looks a bit longer, but nothing to surprise you. It's just simple manipulation. All right. Hence, if you need to maximize the thrust for a fixed component efficiencies, flight speed, compressor specific power, and expansion power, you get the optimum value. So alpha opt, so this is not like the angle of attack. It's not the angle of attack. It's a ratio from here, from this equation for the specific thrust. So if you optimize the specific thrust for constant component efficiencies, so you can get this ratio, the optimum value of that ratio, which is given by equation 9. Right? And if you substitute equation 8 for the optimum value into the specific thrust equation. So after optimizing the thrust, then you get the optimum value of alpha. So you substitute alpha here and here, then you will get this equation 10. So equation 10 is a result of substituting equation 9. So this is the optimum exhaust speed, where eta N is the efficiency of the nozzle, eta PR is the propeller efficiency, gearbox efficiency, then mechanical efficiency of the turbine, and the turbine efficiency. All right. So what we've looked at so far was for a single spool, single shaft engine. Now let's look at a two shaft or two spool engine. So in this slide, so this is a two spool engine. You can tell from here that this engine has two compressors. It has two turbines and one compressor. So the first compressor is driven by the first turbine, or the high pressure turbine, and the low pressure turbine is the one that is connected to a reduction gearbox, and it drives the propeller. And again, from the TS diagram, temperature entropy diagram, you can tell that the maximum cycle temperature will be the temperature at entry to the first turbine, because the first turbine is the one that is adjacent to the combustion chamber. So the hot exhaust that are being expelled from the combustion chamber would directly be in contact with the first high pressure turbine, and that would be where the highest cycle temperature would be. So T04 will be the highest cycle temperature. All right, now that I've explained that part, then you can do a similar analysis as for a single spool. So for the intake, the same equation that we looked at are applicable. And if you come to the compressor, you have the same equation, and you can calculate the power needed to drive the compressor using this equation. the specific work of the compressor is equal to the change in enthalpy, or the enthalpy rise, which is specific heat of the cold air entering the compressor multiplied by the temperature difference across the compressor. Then in the combustion chamber, you use the same equations as the one we looked at earlier on. Alright, and this is, I've already explained this part. And from the first turbine, you look at the first turbine. So the energy balance between the compressor and the high pressure turbine, which I said earlier on that the high pressure turbine or the first turbine will drive the compressor. So the energy that the compressor needs comes from the energy that the first turbine is generating. And if you do an energy balance, you can get equation 11a. And the work that the first turbine generate, which will be equal to a change in specific enthalpy, is given by this formula. But because this is specific, it means you are dividing by the mass flow. And if you do that, you can make a simple mathematical manipulation where you have 1 plus fuel air ratio minus the blade air from the compressor. I'm sure by now this shouldn't be a problem. Okay, and you get equation B. And since the inlet temperature to the turbine is known, to get the outlet temperature, you use this equation. And everything here is known with the mechanical efficiency of the compressor, mechanical efficiency of the turbine, and everything stays the same. And once you know the outlet temperature to the first turbine, you can get the outlet pressure using this relation. And here you are merely applying isentropic relations. Because from here, what you're doing, what they've done to get the pressure is they've divided here. If in this equation T05 is equal to T04, if you divide this equation throughout by T04, on the left hand side you will get T05 divided by T04, and this will be equal to 1 minus this expression divided by T05. Then you use isentropic relation for this part, and you relate it to the pressure, and you get your answer. Believe to be pretty straightforward. Now, if you come to the second the second turbine, which drives the gearbox that is connected to the propeller, you can get the work developed by this turbine, which is usually referred to as a free power turbine. So the work that will be done is similar to the previous, is similar to equation 11b, except that the temperature are those that are between entry to this turbine and exit to this turbine. And here you've got CPFT, which is the specific heat capacity of the exhaust air that enters. That's why there's FT, that enters the free power turbine. So please don't confuse it with other relations. Okay, so now we can, to get temperature 6, so from the equations we've looked at previously for a single spool, the outlet temperature to a free power turbine will not be known. You can't know it in advance because this turbine is used to drive a gearbox, which in turn drive a propeller. So you need to do a bit of reverse analysis. And this is similar to what I've explained earlier. So that this free power turbine is coupled to a gearbox, and this gearbox is coupled to a shaft that is connected to the hub, which has propeller attachment to it. So if you work in the reverse, you can get the power at each section. And I'm not going to repeat this part, but good for your knowledge. And if you do that, you can do what we looked at. We can look at the enthalpy rise across. This is a free power turbine, like the enthalpy drop from enter the free power turbine and exit the free power turbine, because 7 is exit to the no zone. So if you do a similar analysis, you get equation 4 similar to what I've explained for a single spool, so no need for me to explain it here again. And to get this optimum ratio or coefficient alpha, the propeller thrust and the exhaust thrust must be determined. Then the propeller thrust is given by this formula, and the nozzle thrust is obtained by this formula. So if you add the two, you get the total thrust, and if you divide by the mass flow, then you get the specific thrust. Then if you substitute these parts, and where there's the exhaust speed, if you substitute the component for the exhaust speed, you get equation 13, which is the specific thrust of a turboprop engine. And this is a summation of the propeller and nozzle thrust. And if you maximize the thrust for fixed components, so to maximize the thrust, like here, in equation 13, you multiply by MA, then you get the total thrust. Then you differentiate this thrust with respect to alpha. So if you do that, you differentiate the total thrust with respect to alpha and equate the results to 0. That's what they mean by maximization of the total thrust. And you make alpha subject, and after you do that, you give it a subscript, which is the optimum alpha, then to be given by this formula. Quite similar for a single spool, except I think of the square under the numerator. This part wasn't there, but I feel everything else is almost the same. And with this optimum value, if you substitute it into equation 8, which was the equation for the exhaust speed, you'll get equation 15. All right? And I've already explained this part. And yeah, so analog with turbofan engine. So what they mean here is like similarities between a turboprop and a turbofan engine. So a turboprop engine are analogous to high bypass turbofan engine. The propeller itself is an ducted fan with a bypass ratio equal or greater than 25. I feel this part just read on your own. Then the momentum differences between the outlet and inlet core flow results in a core thrust. The core thrust is given by this formula, 16. And if they introduce a bypass ratio, which is the ratio between the core flow and the ratio between the bypass flow and the core flow, then you get equation 17. These equations are pretty easy. We looked at them under turbofan engines, and I've just included them here for completeness sake. And from equation 17, which is the total thrust, if you divide by the mass flow throughout, you get the specific thrust. So which is merely dividing by MA dot In equation 17 you get equation 18, nothing strange. So now let's look at equivalent engine power. So we'll look at static condition and flight operation. Okay, so if you do that, so on a test bench, the takeoff conditions, the total equivalent power in kilowatt is related to the shaft power, also in kilowatt. So, and is given by equation 19, which is total equivalent power at takeoff is equal to the shaft power plus the jet thrust divided by 8.5. So these are some empirical formulas. Then the thrust on a test bench will be given by, on the ground or during takeoff, will be given by the mass flow multiplied by 1 plus fuel air ratio minus the blade air multiplied by the flat speed. Then in operation, the equivalent shaft power is equal to the shaft horsepower plus jet thrust as given by this relation. So equivalent shaft horsepower is equal to the shaft horsepower plus thrust times flight speed divided by a constant times the propeller efficiency. And in this case, the constant was 8.5. Where T is given by this formula, I feel everything is okay. Alright, now, having looked at everything else, we can look at the fuel consumption. And I explained under the introductory part that turboprop engines are, if you compare them with turbojets and turbofan, they are more fuel economic. So in fuel economics, we use the thrust specific fuel consumption, which is equal to the fuel flow rate divided by the thrust. And it's expressed in kilograms of fuel per Newton hour. And for a turboprop engine, the equivalent specific fuel consumption is equal to the fuel flow rate divided by the equivalent shaft horsepower, and expressed in this unit, kg fuel kilowatt hour. And these are the typical values in pounds of fuel per horsepower and the kg of fuel per horsepower. So you can look at the typical values like 0.27 to 0.36 kg of fuel per kilowatt hour. You should compare these values with those of a turbofan and the turboprop. And I hope you will notice that these values are slightly lower than for a turboprop and a turbofan. Alright, so this was my last slide, and I wish you a good day, and hopefully this should make sense after you read and watch the video. Good luck.